So today we will discuss the strain energy concept. Uh, this concept is used in the impact loading. So first of all, we will understand what is strain energy under different conditions. So just explain, if we consider a uh, uniform rod under tensile load condition, and we are going to slowly increase the load. So when we plot the load deformation diagram, load displacement diagram, so it will be like this. So the area under the load displacement diagram, that is the work done. So work done by the load P is the rod elongated by a small dx. So for a differential element having differential length of dx, uh, the work done is P into dx. So which is equal to the area of the width dx under the load deformation diagram. So for the whole curve, we can integrate for the whole length from 0 to x1. So for total work done, we are integrating the load into displacement, and this total work is called the strain energy. So when we increase the load, the strain energy of the rod is increasing. So for this portion, when this is the portion in which we have the deformation is elastic. So if we zoom out this area, so it will be like this. So this is the load on the y-axis, displacement on the x-axis. So for any small portion, the work done will be equal to the area under the curve, which is 1 over 2 P1 x1. So this is basically the area of the triangle. So 1 over 2 of the base multiplied by the height. So load is equal to kx. This is for the from the Hooke's law. The load is equal to stiffness multiplied by the deformation. So integrating for the whole length of the elastic portion, the linear elastic deformation will be equal to 1 over 2 P1 x1, just by substituting for the K, which is the load divided by deformation. So this is the elastic strain energy or elastic deformation. Strain energy density, this is the another concept. If you want to eliminate the effect of size, so evaluate the strain energy per unit volume. So divided by volume, and volume is equal to area multiplied by the length. So P over A is the stress, and dx over L is the strain. So strain energy density is equal to the stress multiplied by the strain, and we will integrate for the whole curve. This is the strain energy density. So the total strain energy density resulting from the deformation is equal to the area under the curve to E1. So this is the total strain energy density. as the material is unloaded, so we previously loaded, and then if we load it up to this point, for example, if we load in the elastic portion and then we unload, so it will uh, reach to the origin having zero stress and zero strain. But if we crosses the yield point and move to this point and then we unload, so the stress will be equal to zero, but there will be some permanent deformation and permanent amount of strain, which is called the plastic strain. So this is the triangular area, this is the recovered area, recovered energy, and this is the elastic energy which is recovered, but this amount of energy that is related to the plastic deformation, so which is not recovered. So remainder of the energy spent in deforming the material is dissipated as heat. So there are some properties which we can extract from the stress strain diagram. Some properties we have already discussed. This is the yield point, ultimate tensile strength, which are used to compare in to characterize the material, also used in the failure criteria. So there are some other properties which are associated with the area under the stress strain diagram. So the area under the stress diagram until the rupture point, this is called the modulus of toughness. So a material having higher, larger this area, you will consider that the material is more tough. So most of the material, if they are ductile, uh, having higher span of this stress strain diagram, they are usually more tough as compared to the brittle material. So ductile materials are considered as the tough material. So the area under the stress strain diagram give us this property, which is called the modulus of toughness. So this modulus of toughness depends upon the ductility. Ductility means that the span of the spread of this curve, right, and the ultimate strength. So it is related to the height of this curve. So higher the height, larger the span, then this area will be increased. If the stress remains within the proportional limit, then there is another property which is called the modulus of resilience. So the area under the curve until the yield point, so this is called the modulus of resilience. And from the previous stress strain stress strain relation, we can say that according to Hooke's law, stress is related to the modulus of elasticity in strain. So this is the stress and this is the modulus of elasticity and this is the strain. So replacing this stress with the modulus of elasticity and the strain, so we will get this relation. Again replacing the strain with the stress, so the strain energy density will be equal to sigma 1 square divided by 2e. That is only for the elastic portion, not for the plastic portion. So if sigma 1 is equal to sigma y, So then we will be strain energy density, that will be called the modulus of resilience. So elastic strain energy for the normal stresses. If an element with a non-uniform stress distribution, so generally the total energy will be equal to strain energy density multiplied by the volume. And when we integrate for the whole volume, so this is the more generic expression for the total strain energy. So for value of u less than uy below the proportional limit, this is the sigma square divided by 2e into dV. This is the elastic strain energy. So this is for the variable cross-sectional, and this is the most general expression in which volume is variable. Volume is not constant. You can say that for different sections there will be different type of volume. So this is the more general expression. But in our case, we will mostly discuss the uniform cross-section. So under axial loading, uh, if the cross-section area is constant, so we can say that A into dx. So for axial loading, for a uniform cross-section, we can integrate for the whole length of the rod. So this will be p square divided by 2ae. So when we integrate it, so it will become p square L divided by 2ae. So this is the total strain energy for the tensile loading of uniform cross section. So the strain energy concept, we will use it in the impact loading. So before that, you will understand what are the relations for the strain energy for different type of loading. This is one type of loading, it is the tensile loading. Now we move forward for the strain energy for the normal stresses, but here we have the beam. So remember, we discussed most of the time in our classes that a beam is an element which is subjected to the transverse loading, and whenever the transverse loading occurs, there are some stresses which are generated inside this beam, and that's most of the stresses that are in the along the axis of the beam. Here are some shear stresses as well, but most of these stresses are the axial stresses which are generated inside the beam. And we know that such type of loading in the lower fibers, there will be tension, in the upper fiber there will be compression in the beam. So these axial stresses are expressed by the flexure formula, which is equal to my over I. So m is the moment, y is the distance of the fiber from the neutral axis, and I is the moment of inertia. So we have relation for the tensile loading condition, sigma square over 2e, but here the sigma will not be equal to p over a because here the stress is related to the moment and the moment of inertia, and replacing this flexure formula and just putting into this, so we will have the total strain energy for the beam under transverse loading condition. So dV is equal to dA dx in the more generic expression. So dA y square dA, this is the moment of inertia. So this moment of inertia will be, this is the I square, so I will cancel out with this square. So m square over 2EI dx. So this is the general expression for the strain energy for beam under different type of transverse loading, m square over 2EI. Here is the simple case for an end loading cantilever beam. So moment will be equal to minus px. So just putting this minus px into this equation, and then we will have this kind of relation. And when we put the length in the x variable, so it will be reduced to p square L cube divided by 6EI. So this is the case for the cantilever being having uniform cross section and having only load at its end. So for this kind of beam, if we have different type of loading, so we will segregate this beam into different cross sections, and then we will find out the strain energy for the individual section, and then we will sum up the whole strain energy. So this is the method, general method. So in this way we can find out the elastic strain energy for the normal stresses in the beam. So this is the normal stresses, remember, normal stresses. We can find out the strain energy for the shear stress as well. Here shear stresses are usually associated with the deformation of the element, the angular deformation of the element. We can see that this is 90-degree element was distorted to some reduced angle and some increased angle as well. So just like the Hooke's law for the normal stress, we can find out the strain energy density for the shear stress as well. So tau is the shear stress and gamma is the shear strain. So from Hooke's law for the shear stress, tau xy is equal to, it is directly proportional to the shear strain while keeping the constant of modulus of rigidity. So replacing the tau xy, which is equal to g and gamma x. It is difficult to write because I don't have the stylus pen. So 1 over 2g, replacing this into this, so we will get like this. So 1 over 2 tau gamma xy, and then again replacing the gamma with the shear stress. So it is just like the strain energy for the elastic limit, having only change of the modulus of elasticity is replaced with the modulus of rigidity, and the normal stress is replaced by the shear stress. So this is the total strain energy for the shear stress. This is the shear stress, this is the shear strain, just like the normal stress and strain, we have the yield point, and we have the area under the strain diagram. So the strain energy for shearing stress, so for non-uniform cross-section, more generic, the shear stress that is equal to tau rho over J. This is from the torsion formula from chapter number 3. So replace this tau xy into this equation. So we will get this type of equation. J is the polar moment of inertia, rho is the distance of the fiber from the neutral axis. So setting dV is equal to dA into dx, so rho square dA, this is the polar moment of inertia, so rho square into dA, this is basically J. So this will cancel out with the square of this, and this total strain energy will be reduced to this expression. So if we have a uniform shaft, so we can simply integrate with this, and we will get this total strain energy. So this is the total strain energy for the shear stress for a uniform rod under the torsion.